Hello everybody, welcome to another stream. How are we all doing? Hey there Ansel, how you doing sir? How's it going? Yes, so today doing a bit of designing because I presented this sort of idea that I had about doing some form of like acceleration structure for ray tracing spheres. And it was sort of going to be joined with the light system and stuff, but like a clustered light system. But it turns out it doesn't quite work, which we'll get into in just a second. And I'll briefly explain the clustered shading thing again when we describe it. But yeah, but it's fine because I've got some ideas. But I first just want to start off by gathering some information from our current setup just so we can feed that into the design. So we take some performance stats and just see what we see what sort of numbers we get. Hey there, Chris, how you doing? Doing alright, right? So tired there, I can imagine all that playing. But yeah, hopefully, yeah. Cool. How you doing, Chris? How you doing? So we've already got some performance metrics, right? They're right here in our face. So I think something to take note is the occlusion is writing 100 and something thousand. No, it's probably not a good thing to use because if they go outside the view frustum, they won't show up. But that's looking about 0.07 ms for about 120,000 probably that are inside the view frustum, maybe a bit less spheres. So, okay, maybe about, okay. So if we times that by 10, that's what it'll be on Intel. So about 1 ms. So it's something to keep note of. So essentially binning into some pixel on the screen, on a texture, like for 120,000. That's one of the metrics I wanted. And the other metric was the ray tracer. So I want to disable that occlusion thing. So we should really write these guys down, probably in some other new buffer somewhere. So essentially, like the occlusion, which can be thought of as sort of binning about 120,000 spheres, is working out at about 0.1 ms. So probably 1 ms on Intel. Right, on that cheap Intel laptop GPU I got. Hey there, Crimson Mania. Awesome, good to hear. Akraz, I'm Kept Payne. Welcome, sir. How you all doing? So there's one more performance metric I want to gather before we go over the design. And that is like, ideally how many spheres per pixel can we trace against? So we should disable that occlusion thing. Because it's actually improving the times here. And I think we'd filled up like 256 of them in a tile, right? So let's destroy that occlusion code. Just get rid of it because it's causing bugs and it's making it faster than it should be. So it won't be a good metric. Let's get rid of all that. We want the occlusion reset. The clear. There we go, a lovely 4.5 ms. Wow, we're still getting bugs. Interesting. Huh. Interesting. But another interesting thing is that the tile bending takes... Yeah, but maybe that's because it does the extra occlusion check now. Here's the sphere bending. Let's nuke this occlusion check code where it looks up in that occlusion texture, which doesn't really exist anymore. But I'm surprised. So I guess the bug may have not came from the occlusion texture itself. Maybe it's this way it sampled it. Something like that. Right, here we go. Now this is sort of bug-free now. Except for when it fills up the number of spheres per tile. Doing good. Awesome. Good to hear, Chris and Mania. Yeah, not doing bad. Just been quite focused at work trying to fix like one or two bugs. But I've tracked them down and fixed them now, but they're just like real pain in the butts. So it's kind of tiring past few days. Happy accident maybe. Yeah, it's a weird. I don't know, I think it would have cleared all the textures, you see. So I don't know why it was doing it. Like the same bugs that are appearing. So right, so here's our metric. Here's our performance. Let's just look at the ray tracing code just to make sure it's not doing anything nonsensical. Right, it's doing this, where it's trying to do some sorting, but it doesn't actually use it. It fills up the sort keys and uses the sort keys. Should we get rid of this sorting thing that it's trying to do? Yeah, this was me trying to do that sort thing, but we'll figure it out. Maybe we'll need this in the future. To be fair, this code didn't even work, so let's just delete it. Right, let's look at these numbers. Surprised we didn't get a crash, to be honest. Whoops. Hey Skarsh, how's it going? How's it going? Tile spheres. Oh, there's a base sphere. No, there isn't. Yeah, there is. Base sphere for the tile. Yep. Got to add that there. And Bob's your uncle. Boom. Okay, so now let's just double check we're not doing anything else that's silly, because that upped it by about 0.5 ms looking at it. Okay. So anything else that could be really silly in here? So we can just get a metric on like how many spheres we're looking at per pixel. And that'll help us design our acceleration structure. So we're just doing some standard like see what tile we're in to get the array of spheres. This is some camera stuff which probably compile out. This gets the ray direction for the pixel, goes over all the spheres, picks out the sphere for that tile. This is debugging code to see some bounds of the spheres in screen space. Ray 3D versus sphere. Yeah, so this was pretty Yeah, this is fine. Yeah, and then we do this near miss thing, right? Where we actually do anti-aliasing. So if we miss it, we see how much did we miss by? We missed by a pixel. Well, we'll do some anti-aliasing. It's pretty cool. It's got a few bugs though, and I do know how to wanted to fix it, but there's no point fixing it yet when we're going to be changing it anyway when we do acceleration. When we have an acceleration structure, right? So I want to comment that out and see how fast it goes. Going pretty good. Thank you. Awesome. Awesome. Right, let's give this a launch, see how much better it is. Right, so that dropped it down by about... There's not that much that it adds, but it's good savings regardless. It's... on average, it's about 3.8. We put that back. .5 is average, so it saves about 0.7 ms. Okay, so let's jot this number down quickly before I forget it. So ray tracing 256 spheres for each pixel. Now this is only for 1280 by 960 because it's not a full 1080p screen, right? So that's another thing to keep note of. And obviously on Intel it's 10 times that. Hey Provod, how's it going? Thank you so much for the raid, sir. Appreciate it. How did the stream go? Welcome, raiders. We're just getting. We're effectively ray tracing a whole bunch of spheres. We've tried we've tried to bin these in screen tiles and just see how fast it goes. Here's our test scene. It's about 120,000, 140,000 spheres. We're kind of getting 4.5 ms right now. I want to try a different kind of acceleration structure because I realized that this isn't going to work with basically lighting and shadows. So we're going to try some more three-dimensional acceleration structure. And so we're going to have a look at that today, this stream. Yeah, the spheres are touching, and they wobble a bit as well. They got some anti-aliasing as well, but this is a little bit buggy in some cases. Yeah. Also, I might eventually offset them as well, so they're not just in a grid. You know, we'll see how that looks. But yeah. Yeah, we'll do a custom acceleration structure. We're doing it all in software. So we'll probably do a BVH, but we're going to be constructing it in a very specific custom way because we'll basically take the limits of the world bounds, I think, into account. Yeah, so the view space binning won't actually work. And I'll get into why this won't. It's got such a cool name, right? You know, using Froxels, but this won't actually work. It works great for light binning, but it doesn't work good. I want to put the spheres in there. And we'll get into that in just 1 second. I'm literally just gathering these metrics so we can feed into it. Yeah, BVH is the way to go, definitely. I was thinking of Octree, to be honest, but that didn't. And then I was sort of just, yeah. And then I realized how many layers I'd have to tunnel through. And I was like, nah, that ain't good. So, yeah, we'll probably just do BVH. Hello, how long are you programming? I don't know, I've been programming for, let's work out how old I am first. About 14 years. Do you know how to do BVH GPU construction? Yes, I've thought about it, but we're gonna be planning it all out today. So we'll go over from like 0 to hero, you know? It'd be good. Spatial partitioning, woohoo! Yeah, I was thinking about the BSP trees as well, like binary space partitioning, but that didn't. That was, yeah, probably not as good either. Long enough been alive, oh no. Yeah, I saw the NVIDIA paper, but they said it took many, many milliseconds. But and also theirs has many steps. They want to make a tree which is I think I read the paper a bit last night. They make a very sort of untied, like unoptimized one, and then they sort of patch it. So I think I can do something bespoke. Like I think theirs is kind of a general one. I want to see if I can design a bespoke one first. If I get stuck, I think I'll look around some more. Because I saw theirs and they said it was taking like 4.5 ms to do. But maybe it's because of the high data set they had like 40 million triangles. I don't quite know. But yeah, welcome folks. If you have any questions about the project, feel free to ask away. So ray tracing is about 3.5 ms, 256 spheres. Yeah, for each pixel is about that number. So ideally we want to, if we half it, ideally be like 1.75 ms, half it again, we're maybe looking at probably something under it, like, just under 1 ms, right? Ideally. So with an acceleration structure, maybe we could do 64 lookup sphere checks, right? So we'll see. So obviously on Intel, on Intel, this would probably be 3.5 ms. Now I say that on Intel because I've got this Intel laptop where we just got this thing up and running on using my custom C compiler, and it kind of would be nice to see if you can get something of very low quality working. But yeah, I don't know how fast it would be. So, but it's just good anyway, just as a thought experiment. Obviously, we would turn off a lot of the heavy ray tracing stuff and do a lot more lower resolution. So, but it's just good to have it there as a thing to compare against. 12K objects claim to be. And before on Nintendo 64, 60 FPS. Oh no, that'd be insane. Space partition is one of the things, and you do the same thing, but other primitives. All right, yeah, it makes. Yeah, I think this is the one I saw. Thinking parallel, tree construction. They got a paper for it. Oh, maybe I didn't read this one. So they're using like Morton Z curves. So also as well, I wanted to do a three. I want to have a limit of three levels deep. Yeah. Right. So I'll look at this later. I can't be able to look for it now because it'll just. I got an idea and I want to sketch it out, and then I think I'll look into it later and see if I got it. But thank you for that. Appreciate it. Right. So we got our numbers, I think now. So ideally, we're looking at like we want to spend like maybe 64 spheres per pixel at most, maybe, so that'll get us about 0.9 ms, right? Quick maths. Right, maybe. If we could do less, it'd be like half of that, right? I'm not sure about construction of the BVH though. So when we tried to put, so this occlusion texture that we did about 120,000 spheres. And it was about 0.1 ms to put a single pixel on a texture. So we're going to kind of be doing something like that, but then doing some other steps afterwards. So yeah, hopefully we can aim for about something. It is linear. Is it linear though? Yeah, I think that BVH thing, they did say on the paper, it said it's scaled linear. There needs a radix implementation to do the modern codes, right? There. Yeah, I think you can get a radix sort from AMD, or maybe there's some good one elsewhere to copy. Right. So I think, and then like ideally we want to spend maybe, less than 1 ms to build a BVH. So looking at maybe 2 ms for the whole, like this is ideally, but we'll see where we actually get to. So this is the sort of aim I reckon we'll go for. So what we're thinking about doing, so we basically bin our spheres into screen tiles right now. So we have screen tiles of about 16 by 16 pixels, and each tile points to like an array of spheres. And there's about 256 spheres that sit inside this buffer. At most, it's such a big number, it's really silly. So you've got about 120 times 160 for the current resolution we're doing, which was, about that many times 256. So you got about about 5 million spheres pre-allocated. And if you overflow this buffer, you get artifacts because you're binning it into these tiles, these screen tiles. So, yes, these tiles obviously cover the whole screen and blah, 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 blah. So we basically wanted to come up. What else did I do? Yeah, then I did some form of occlusion buffer. So we have like our screen tiles, right? And our essentially, well, okay. We have like our, where was it? Yeah. So we essentially have our spheres on the screen, and we'll build up like this depth, this rough estimate of a depth, which is really cheap to build. And you would sample a single pixel back and see if your sphere that you're trying to render is behind that depth. And if it is, you just want to render it. But this would be very limiting to the view that you're rendering from. And the problem is, if you basically do any lights, you typically want to either shoot some rays, if you're doing ray tracing, from the light, or you want to shoot some rays towards the light, whatever way you want to do it. Or you basically render a shadow map. And that's effectively having another view frustum from the light's perspective into the scene. So we've got this occlusion data, which is specifically for the main rendering. It won't really benefit would have to keep, like if this is occluded and it's not in the screen tiles anymore, like it's not gonna be, we have to have a different list of spheres around, and it just takes up a lot of memory. You calculate in different acceleration structures, and it's not really ideal. So we want to try to make a single acceleration structure to rule them all, really, to solve the lighting problem and launch it from the main perspective as well. So we thought about, doing this sort of clustered shading thing. I'll drop a link to this in the chat. There's also like a YouTube video I was looking at too. And the basic idea with this is that you have this frustum grid, which you can basically goes in like a 3D texture. But it could go in a 3D texture if you wanted to. It could be a 3D texture or just a 3D array or whatever. So you have this frustum grid And you're supposed to bin lights into this frustum grid. So you can call them froxels, right? These are froxels because they're frustum voxels. So you're supposed to bin the area that... so if this light affects this area, all of these froxels will have a list of lights. And it means when you do like your forward rendering and do the lighting calculations, you can have lights that are not affecting your pixels basically. So you can just skip these lights. So if you have a whole bunch of lights, you might have like an area light or whatever. Sorry, what's it called? Like a point light. You have a point light here or something which affects these froxels. All you have to do for these, when you have a ray that sort of lands here for some reason, you only have to do the lighting calculation for this light, right? And you can skip this one and this one. So this sounded quite ideal, and I was like, you know what, I can just have another list for spheres that go in these froxels. But it becomes a big problem. Let's just catch up with chat. Meanwhile, you guys can think of what the big problem is. I'm not use BVH4. Can you build it once and just update any changes, or is it better just to rebuild from scratch? Yeah, I think so if you look at the new ray tracing APIs, there's a thing called refitting, or in Vulkan it's called update, which is a very generic word, but it's called refitting in other APIs. And the idea is that you basically only update the positions. So if you have like a mesh that animates, you only update the positions, and then it recalculates the BVH. But it means that it won't actually add any more triangles or take away triangles from the BVH. It will just simply update their positions and then refit the bounding volume hierarchy. But I don't think we're going to be doing that. Yeah. Like the list of occluded objects, if the sphere is on the list, don't do the light thingy. Yeah, exactly. That's like it, yeah. Instead of ticking myself, oh, okay. Yeah, froxels are the best name. So I will miss froxels. Froxels will be best. Well, actually not really, because we might still use this for the lighting, to bin lights. So, but in terms of like, we have one acceleration structure for binning spheres. Hey Egotist, how you doing? Happy Tuesday. So, here's the problem. Well, here's not a problem. I have a light over here, right? It's a light, I promise. It's not an eye, it's a light. And it casts light all the way up to there. And so you can still do your shadow map, right? And only if it affects these froxels here, and maybe that froxel, and maybe that froxel, right? Seems good, right? Okay, I have a sphere here. Wait a minute. You have a sphere here. This sphere doesn't get binned inside any froxels because it's outside of frustum, outside of your view frustum. So what happens is when you do this shadow map, you'll be missing this sphere because this sphere wouldn't be binned anywhere. It doesn't go in one of these bins, right? So you basically have missing information for anything that's off the screen. So any shadows from above that come from above, any from the side that are off the screen, you're simply not going to get. So that's a big problem. So effectively you've just made a screen space lighting system, which is not, well, you've limited your lighting system, which was not limited by screen space. Now I'm limiting it to screen space because your objects are only binned on the screen. So clearly we've got to have a solution where it goes off the screen as well, right? So effectively, you have two different approaches you can take. You effectively now we've got to build a sort of in-world acceleration structure for our spheres, and that's something we're going to be doing. So I guess let's just go ham and draw ourselves a new thruster. Right. I'm doing all right. How am I? Awesome. Good to hear. Good to hear. Yeah, not doing bad. Not doing bad. Pretty. Yeah, got a bit. Been a bit tired the past few days. Just been sort of hunting down some bugs at work, but they've been hunted down now and destroyed. So it's all good. But yeah, some of those. But other than that, doing all good. Doing all good. But yeah, I've also been trying to think about this on the side as well. So we've got a view frustum. Now the idea is that we need, so there's a few ways you can do it, right? There's this thing called an oct tree. So an oct tree is a bit like a quad tree, but in 3D, right? So you could go with this solution. So ideally it would be bigger than the view frustum. Let's just draw it a little bit bigger. So we're not going, so it's an in-world thing, right? So you can still cast shadows and all that. So imagine it, we're looking top down, but you would basically do another layer underneath it, right? So with an oct tree, it's like a quad tree, we divide it into 8 pieces. So imagine if we have a sphere. Just over here or something. Oh my days. Divide. So there's obviously 8 nodes here. There's underneath ones, right? And then you want to divide this one again into 8 more. Then you probably want to divide this one into 8 more. And it's up to you how much you want to keep dividing. But effectively, this is how an oct tree will work, right? You effectively, like you might have, I think the spheres will be way smaller than this sometimes. This is actually quite far away from the camera, so it might be this big. But yeah, so you need to keep subdividing. So you basically check less spheres. So, you know, you might have, it's a way to effectively, when you launch a ray to that sphere, like ideally we should have a bunch of spheres drawn on the screen. Like imagine if you have hundreds of thousands of spheres. It means all you have to do is sort of like check this box. And it's like, oh, this box has no spheres in it, so you can actually skip it. Then you just sort of check this box. Okay, it has some a it has another oct tree, a tree of eight nodes in it. These ones are all empty here, and then you traverse down another level. So you go into this one here, and then you'll sort of like realize that these two. Wait, sorry. Kind of described that a little bit wrong. You realize these ones are all empty. Your ray only intersects with this one and this one over here, right? This big one here. So you'll go into this one, then traverse down and be like, well, my ray intersects with this one here. So that was 3 traversals to get through. So you would essentially you wouldn't have done axis line bounding box stuff, you would have done something a little bit more like, I know the size of this, so I can sort of like, traverse through it. And also it's in 3D as well, so there's actually a Z component to it. So it would have been more checks as well. But it's just a 2D example, I guess. And then you would get into here and realize that it's like, it's not that it's a leaf node. I guess you might have spheres and like, yeah, I'm unsure about how, yeah, I'm unsure. But yeah, maybe I think let's just say it's a leaf node, so there should be a bunch of spheres in here. Let's just say it that way. So then you just check the spheres inside this box. So ideally, you should have less checks. So I guess imagine, yeah, if this view was filled with like hundreds of thousands, you would essentially it allows you to skip some form of empty space and also minimize the amount of spheres that you end up checking, because you only would check with inside of the regions that you overlap basically in 3D space, and you would not check any spheres that are in these spaces, right, if there is any. So that's the basic advantage of this. The problem I found with this octree when I was thinking about it is the fact that the way that you skip space is at best half of the current node, and you can't skip any better. And if this is subdivided, you have to then go and tunnel inside all the ones that so I have to sort of go inside this one and then sort of, is there anything inside here? No, there isn't. And then I have to go inside here, check if there's anything inside there. No. Anything inside there? No. Come back out again, check inside this whole box, realize I collided with this, and so on. So it's a bunch of like tunneling in and out. And you might go down so many layers and back up layers, and I think that's not, it's not good. And there are different approaches you can take with octrees. Maybe having them more local and having a different approach outside. But yeah, I don't think this is a good suit for what we're doing. Do you need the frustums to do your binning, or can you have a condition to bin without it using a light? Do you need frustum to do the binning, or can you have a condition to bin? Yeah, I'm not sure what exactly you mean there, campaign. Yeah, I'm not sure exactly what you mean. Could you possibly rephrase that? Sparse octrees. I'm not sure what you mean by sparse octrees. Now, what does that mean? But yeah, I know you can sort of like maybe flatten. Hmm. I'm not sure what it's saying here that makes it different to a octree. Like, by the word sparse, I mean it's, you're probably saying it's not allocated, but that's what an octree kind of is, right? Therefore, an octree doesn't have the nodes allocated, that it's not. I don't quite understand what it means. Can be bigger and smaller volumes. Right. Oh, so it can just, rather than tunneling through each layer, you could just point to something which is smaller. Right, so there's less tunneling. So, okay, I see what you're saying. So rather than, in this case, there's only one, and these are all empty, right? And even these are empty. Maybe, actually, it doesn't matter. Yeah, if all these are empty, you can just tunnel down to this small volume. I see what you're saying. Yeah. Yeah, that's some way to do it. But again, you get that skipping problem. Yeah. So the other there's a few other approaches. We'll go over the other approach we're not going to do. And first, let's get the music back. Um, so the other approach we're not going to do is a uniform grid. I think we're going to use sparse grids. You could essentially just. So I think we might use this to build our BVH, but we're not going to use it to actually accelerate anything, because I think it requires too much, basically scanning through arrays and not really skipping too much space. So the way you could think about it is you've basically got a outer, like a, essentially you think of it as like a cat, like a, it's just layers of indirection. It's just lookup tables, grid lookup tables. That's a good way to say it. So you've basically just got some form of like grid. Maybe in your world, the amount that you want to support, you've got like this 4x4x4. And then inside that 4x4x4, where you've got, you basically have an inner grid where it goes another 4x4x4 or something. And you basically just, you could probably have a bit set to say something like, you could probably have like a bit set to say that, you know, this cell has something, so you don't actually store any. You know, you could probably like safely assume that not every cell and subcell is going to have information. So you could probably pre-allocate like a little buffer, which is like, this is the maximum number of cells we support with spheres in them. And then you sort of have a bit set to say which ones are actually set. So I guess when you launch your array from the view, you'll like you'll basically scan through the bit set. And you'll be like, you'll check if the bit is set, no. Next one, no. Obviously in 3D, so there's probably some extras. And is this bit set? Yes. And then it will tunnel down into the next grid, right? But again, this has the same problem of the octree, where you basically have to jump in sort of linear, what's the word? You can have big jumps, but they're sort of they're fixed big jumps, and you have to, you know. But this is good because it's a bit set check, so it's probably like you can fit them all near each other in memory. So it might be kind of be quite good. But yeah, so this is kind of a interesting approach, but I think you could do better. And so that's what we're going to go over next, which is the BVH. Please don't call it a tensor. It triggers my maths. Jimmy's. Right. I see what you're saying. 3D. Yeah. Yeah, there's some. Yeah, there's some also. You could also. Yeah. If you knew sort of some information, you could do some skipping here. It's not a bad idea. Well, yeah, something could be in the way though. But yeah, you could definitely do a lookup at a location with this system. But it's the same with any system, really. Yeah, so that's the problem, is going in and out of all these structures. It's quite, yeah, it's quite silly doing that. So the way you can do that is you've got to minimize the number of levels, right? So you could design this system where you go, oh, we only support going too deep. But if you only support going too deep, you're gonna have more spheres in the cells because you haven't broken it down. So you kind of got to justify another level to really break down the number of spheres. This all depends on how many spheres you want to render. So here's the sort of approach that we want to take, and we'll go over this one, briefly describe it, and then we'll do a little bit of like, what are we trying to render? And then I think we'll actually get into, yeah. Anyway, let's just do that. So the next one is a BVH. So what bounding volume hierarchy is essentially, let's just finish this tea. So what bounding volume hierarchy is, let's get some spheres going. Actually, you're going to draw more spheres this time. Right, I want to do a poor example of it, but let's go. So the bounding volume hierarchy is something like this. Obviously, these should be more snug, right? But again, poor example. So the idea is you might have you basically can just place them. I'll do another sphere just to make that better. Right. So the basic idea here is you can skip. Just launch the ray. Pew. So the idea is, instead now, you test against some axis line bounding boxes. You go, oh, did I hit this one? No. Obviously, it wouldn't be drawing a ray there, but yeah. Did this ray hit this? No, it didn't. Did this ray hit this? Yes. So then you tunnel in. You've got two things to check. Did I hit this? So hopefully you check this one first. Yes. Then you tunnel in. You could have checked that one, missed. So you tunnel in, and then you say, and then you've got two spheres to check against. So you just check that one, and hey, I got hit. So the whole idea here is you basically can get some, depending on how you do it, because it's a very sort of dynamic. It's a very dynamic, it's a very loose and dynamic sort of data structure, right? It's just sort of, you're grouping things together, and sort of how do you group those together when they're near each other, but what is near? And what happens if you introduce something that's over here? How do you decide to group these all together like this, and then this one like this? And why don't you just do one big box instead? So it's quite difficult to decide how to do that. And you also have to do it fast and maybe deal with tons and hundreds of thousands of spheres and stuff, right? And so the idea with this one is you want to basically keep it as kind of balanced as possible in the tree. You want to sort of say, you like on your top level, you don't want to be searching through hundreds of checks. You kind of just have to do a few of them. And then same with the next level, you don't want to be doing hundreds of checks in there, you just want to do a few of them. So you got to balance out the number of levels that you'll have, and sort of you want to find a number where it's like, what's the number of checks I want to maximum number of checks I want to support in each level before I get down to including the last level where I check my spheres, and take that worst case and sort of see if you can balance a tree out for that, and that would be your worst worse performance basically, but hopefully do better. So this is what we want to try and achieve. But it's something to take note. We've done axis line bounding boxes here, and you see here on this sort of after this top level one, there's a sphere here which is loose, and it's not inside another BVH. So this is an axis line bounding box, and this is a sphere. For the purposes on the GPU, we don't want to be doing different shape checks, because if not, there's a switch state or an if statement or a switch statement, and you have to, some of your threads are going to, you basically execute both sides of the if statement. So that's not good. So what we'll probably do is have it use bounding spheres rather than axis line bounding boxes. So instead we'll do a bounding sphere, which will, I don't know, probably yield somewhat the same, might be a little bit worse. Like in this case, it'd be worse. It'd be a lot bigger. But anyway, so that's something to take note. So in a BVH, own rules on how you group them. Yeah, so you need to figure out how you want to group it, basically. So the way we're probably going to do it is we're probably, as I said, do like a sparse grid, because we don't know where our spheres are. Our spheres could be anywhere, and they could be animated. So every frame, we're just going to blow our spheres into some sparse grid. And then from there, we'll do some intelligent build. And then that way we could probably, so I think let's talk about, okay, what's the next one I want to talk about then? So what sort of are we trying to render at its core? Well, we're trying to render a bunch of spheres, right? I want to build models out of spheres. And, so I think let's just compare our sphere to a triangle. The best thing about building something out of a ton of spheres is it could have the illusion of having some form of volume, right? But as a downside, first of all, I've got to make the rendering look good, right? When you have tons of spheres next to each other and all that jazz, right? But also it just takes up far more space than if you just rendered the surface area using triangles. And these are trying to be triangles, by the way. And if I just had triangles go around the outside, the amount of triangles for surface area would, wait a minute. That's a really poor example. Imagine if all you needed to do was draw these massive triangles, which didn't really, that's in the background, and then you're sort of doing like this one. Yes, imagine if all you needed was these massive triangles. Very poor example again with these drawings. So the idea with triangles, you only draw on the surface area. You don't have to draw a whole bunch of little spheres in the middle. Like imagine it, okay, let's draw another one. Or it's just hard to draw a bunch of spheres just quickly, but so if you have this sort of volume here, and say if I select some form of sphere size, which is just very, very, very small, and I fill up a whole area like so. I'm getting tired now, so this is all you're getting. There you go. So if you wanted to like draw this out of triangles, you're like, no problem, mate. Completed it. And obviously each side, right? And obviously goes into dimension, another dimension. And you'd be only representing the surface area. You're not representing these sort of, doesn't have the illusion of having a volume on the inside. So the reason why I want to have this is maybe I can see it having some form of animation, and the spheres actually are not still. And also they're probably not aligned in some form of grid. You might sort of, when we have this custom sort of drawing thing, way of making models in the game, we might place them down in some form of grid. So when we save it out, and we can probably compress it better, all this sort of stuff, and it's just more simple, right? But when we get it in game, like they might be slightly offset. Every other one might be slightly offset by half or something. I don't know. And also when you're moving around, this might be very sort of physicsy, and they might move around. So when you have holes that appear, you see sort of the inner spheres, and it appears like it has some form of volume, unlike triangles. But then you start to have a bit of a problem where, you know, if you have like, say if it takes 100 of these little spheres to make 1 meter in your game, right? So if they're like 10 centimeters, sorry, 1 centimeter, so like 10 millimeter for some reason. So if it takes 100 to fill up a whole meter, you've then got tons of tiny spheres like on the inside, which are probably not going to get shown, and all sorts of stuff. And so I think what I want to do is have a restriction when we paint these guys down. I want to instead do something like this. So we'll still have small spheres, but what's going to happen is they'll only be small on the edge, and I don't know exactly how I'm going to do what I'm going to do, like what the exact algorithm is, but the idea is on the inside they'll just be bigger. So obviously the bigger these models are with more sort of area inside, you just have bigger spheres on the inside, and towards the edge they will sort of break down into the smallest units gradually. So this is how we're going to solve our problem, where we can have kind of small spheres so you can get the detail at the edge of the model, but on the inside we'll sort of make it so the spheres are bigger, and therefore when you're trying to bin these in these, you know, BVHs and stuff, hopefully we're going to dramatically decrease the amount of spheres we're actually going to be rendering and still get that detail. But yeah, we'll see how this goes. So we'll Cole. Yeah, but how are you going to cull it? Like, the only thing you can cull is if you have, like, these are going to be not on top of each other. So there's going to be holes. Past a certain layer, because you can see anyway. Maybe, but you might see it. Like, how are you going to calculate that? So the only way I can see culling stuff is if you have another model with bigger spheres come over your smaller model spheres. That's when you could probably do some culling, but it's at a cost of how do you do that, right? Because you've got to do a bunch of sphere versus sphere checks, or is sphere inside of sphere checks. But you could probably break that down while you're building the BVH as an optimization. So that's a bit of context. So, right, how are we going to bin yeah, so if we have our BVH, basically, if we have another sort of camera or light, for instance, and you render like a shadow map, or you want to shoot some rays from the lights onto the scene or something, you can shoot your rays out and see if they hit the, you know, the bounding boxes and stuff, or the bounding volumes, which would actually be spheres, but anyway. Okay. So, yeah. So we've got this number here of 64 spheres. If we did 64 spheres per pixel, we could be looking at around 1 ms for this resolution that we're doing at the moment. Obviously, we should be doing higher resolution, but there you go. So ideally, when we have our BVH, we need to sort of like balance it enough to the point where, so I want to have a restriction where we probably only have 3 layers. So 3 layers of BVH. Yeah, something like this. And it just means in our bottom level, we should probably have like we did there's not really a lot 64 spheres, because I can imagine having a 4x4 by 4, and that'll get you 64 spheres anyway. But maybe it might be fine. So, yeah. So essentially, so the way I'm thinking about doing it is we'll probably do that sparse grid thing, right? Because remember I was looking at that MIP level occlusion, we binned into a bunch of MIPs, 120,000 spheres. And yeah, so I think what's going to give us a big win is reducing the number of spheres. So we need to have good lodding, like LOD selection. Obviously, if the sphere is not going to be viewable, just don't bin it, like from the view for us. If it's not, yeah, be visible, just don't bother binning it. What else? Okay, so good LOD selection. Good. Yeah, so just reducing the overall number of spheres, basically. And then in the editor, we need to make sure we have enough volume. So the volume been taken up by bigger spheres. So it should be possible, I think, to maybe have around 100k. We'll see. I've really just got to test it out, to be honest. So that says if we did 100k spheres, it's about 0.1 ms, which is actually kind of cheap to just bin it inside this sparse grid. And then to build the BVH on top of that. So hopefully we're looking around maybe 1 ms to build that BVH, right? So what we want to do is have some form of sparse grid that's bigger than the view thruster. And this would be our sort of our maximum range. So how are we going to calculate this? So you could probably have it preset. It really depends on the game, right? We don't know what game we're actually making yet. But we should have some tweakable numbers that allows us to sort of like define this sort of space. So this means if we have some spheres and then like a light or something, like over here, that still happens to be enough to be bright enough or whatever to go inside the view frustum. Something like that. Then it will still cast shadow onto something. So what we need to do is probably like we probably need to find like a light, the furthest light which still projects onto the view frustum, and then sort of just wrap the box around there, something like that. Yeah, something like that will do. And maybe we'll have some maximum distance and just ignore the lights that are too far out. So I think what we want to do is basically have like a sparse grid which will allow us to define which will allow us to essentially like bin the spheres inside this sort of sparse grid. And I don't know what sort of number it is, but imagine if it's like 4 by 4 on the top layer. So it's literally exactly what we just saw earlier. You know, this will have like some form of inner grid. Or it might be another 4 by 4, just for this example. It's probably going to be different numbers. So essentially it'd be a redirection table, right? Where this cell is anyone that actually takes up any space, and the rest of them don't take up any space. You know, these ones only take up space as well. And we could probably, as I said earlier, just allocate some form of maximum number of sort of cells and maximum number of spheres. And if we just overflow, I guess we'll get some artifacts, but we should probably find some upper bound that's good for our game or something. So you're essentially going to bin your spheres in these cells, and we'll probably go down 3 levels or 3 sort of layers. Yeah, so what would be a good idea exactly? Now, I don't know what we should do exactly for this case, right? This sphere is bigger than sort of the lowest tier, so you might as well just stick it in the, like this just might as well go inside the top level one, so might as well not subdivide this far. So yeah, we should probably be like, oh, the sphere is this big. It's bigger than the cell. Like what sort of cell is it going to, is it smaller than? And then just bin it in that level. Obviously, if it's bigger than the biggest one, we'll just stick it in the highest resolution one. But yeah, something like that. So this way, so we'll probably dispatch over all spheres, and they just basically try and bin. They first look in the top level. If the top level doesn't have anything, damn it, I keep doing that. If the top level doesn't have anything there, it will. Well, first of all, see if it will fit into. I think each cell is going to have a list of its own spheres, and maybe we can limit that number. Maybe we can go, oh, we only support 8 spheres per level or something, right? Per level, something like that. And then we can bin it. So this one's going to go. This one's going to be like, oh, okay, I'm bigger than the sort of next layer down, so I don't need to subdivide it anymore. So I'll just go into the list for this cell, and you'll probably set a bit set to say, oh, this one is actually used. But if you have like a small one, proper teeny one, this one will be like, oh, I'm bigger than the next one, so I'll subdivide, right? So I'll subdivide everything up. And I guess when you're doing this, you need to make sure another thread is not allocating this at the same time, right? Or something like that. And I guess the other thread will have to wait for it or something. Yeah, it'd be something silly like that happening. And then I guess, you know, we'll realize, oh, it's smaller again, so subdivide again. And you probably store a maximum in each of them, like, I don't know what the number would be, maybe 8. So we should probably do some maths to sort of figure out, like, given we have three levels going all the way down, what's the sort of maximum we can theoretically hold with a limit of 8 per node and max number of nodes or something, and how many sort of nodes we're looking at. It's probably a good thing to do. Can you set the maximum grid division based on outer level's distance to the camera? Sort of like dynamic LOD. Outer levels distance to the camera. Right. Max division. Right, so what you're saying is, like, these ones that are really far away, chances are they're going to be big anyway. Is that what you're saying? So a bit like this one where the Froxels are bigger. Is that what you're sort of saying there, RCT? Threads per array or threads per tile. So this, we're not launching any arrays yet. This is the binning process. So it basically just means, so when we bin them into this, so when we start off, the problem is we just have a bunch of models, and we just have a bunch of models, and what else is the problem? Yeah, we have a bunch of models and positions for models, and maybe each model has clusters. We haven't really sorted that thing out yet, and maybe the animate as well. So we have to basically get them into some local positional place, so we can sort of do some comparisons to sort of build a BVH in some kind of optimal way. At least we hope, right? So the idea I'm going to start off with is the easiest thing is grids, right? Grids are the best sort of tool for programming. So if we just basically have a sparse grid, so we could use this for ray tracing, but we're not. We're going to essentially bin them in this sort of local space, and then we can basically keep note of using a bit set of which ones are actually used. And then and then after we've got them all binned, we can go over all of these and sort of determine how we want to build a BVH. Maybe we've only binned one here, but we've got like another one here. Like, so we might just we'll go over all the lowest levels first, and we'll be like, oh, this one's only got one in it. So it's like, well, we might as well just get rid of this. And then we get rid of that lower level, and then we've got only two in here. And be like, oh, we've only got two in here. So let's get rid of that. Obviously, those will be in different dispatches, because we'll probably do all purples first, then all blues, and then all greens. And then when we have our sort of spheres in a grid, we can sort of find the most optimal bounding volume, which is a sphere, around it, right? And that's the basic idea. And then we can get the hierarchy from that. So that's the basic loop. So yeah, something like that. Yeah, so that's an interesting approach. So what you're saying is you can determine that the cells that we subdivide are higher close to the camera because you're a lot more likely to get the smaller little buggers near the camera. That's good, isn't it? Yeah. So you should probably... Yeah, that's an interesting idea. Man, that's a good thing. Right, so I think we should start jotting some of this down. Or we could just start writing. No, I think we should write our plan, because there are some hairy... Because we could be like, right, rather than going over all spheres and binning the spheres, maybe you bin the models first, or maybe you bin the models clusters, and then you take the clusters and bin those out into spheres, and you avoid the atomic adds, right? We can get less atomic, because this will evolve some atomics, and then waiting for stuff to create sub areas and stuff, kind of crazy. Whereas if you could bin it into the areas, then you can sort of do a local, you can make a dispatch own a whole sort of area and then do the sort of work on its own local area, which I kind of listed in my previous thing on Discord when I was thinking about how we would achieve this thing over here to the right. So sounds almost like nanite, something like that, and a balanced sphere per model. Yeah. See, I don't want to. In my BVH, I don't have the idea of a model. I don't have the idea of a models cluster. I just want to have spheres. And the reason is because then I could theoretically, if I have two models on top of each other, we could theoretically maybe get rid of some spheres. We can be like, oh, this model has a massive sphere and there's a bunch of little spheres inside. So we could probably get rid of those, right? And I don't want to have the sphere owned by it. It just doesn't feel like a good linkage. Like, imagine if I had 1,000 models on the screen. You're implying a hierarchy that doesn't need to exist, right? I've got 3 levels, and you're implying a hierarchy, and the model also has clusters, probably. So yeah, I think I just want to splat it out. And also, when you animate it, the clusters basically won't make any sense either. The banner sphere could include its next animation step, maybe. Ooh. Not sure what you mean by that. But yeah, I think we want to do the animation. Yeah. So if we bin them by model. No, because the model needs a bounding box, and if you do the animation, it could exceed the bounding box. Yeah, I think we'll think about that later. But we'll think about it from the perspective of doing it fast the first time with what we know with static models for now. Right. So I'm thinking about we're going to bin models. And the reason why we bin models is because 1, it's less data, and 2, we're doing atomics. From what we knew from the initial tile binning, if we have 2 threads which try and atomic write to the same place in different compute units, you've got to deal with these threads communicating, and it's a big pain in the butt. And basically it creates very noisy GPU performance, very spiky performance. So what we want to do is avoid that. So we're going to so you avoid it by just doing less of it, right? It's unavoidable, but you can always do less. So here is the plan. Let's go into the Discord, I think. Another plan. So this was my previous plan with a clustered lighting. We'll probably do a very similar thing. So I had this sort of idea with this one. So here we go. Yeah, for those who are interested in Discord, there's a link to it as well. Where we sort of have discussion about stuff outstream as I stream. I also post up thoughts and stuff on here as well. So I guess this would be the sort of BVH construction plan. Maybe it's not a good idea to chuck it in Discord first, because I have a feeling if you press the escape key, it deletes stuff. No, it doesn't. Okay, that's fine. You know, let's do it in Discord. Right. Dun 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 dun. Right. So the first thing is we want to, maybe it's better. It feels cooler in Vim, doesn't it? Right. So on dispatch, we'll copy it over. You know what? Let's do it in Discord. I can't be asked. Let's zoom in hard. Right. So one is on dispatch over all models, right? We'll dispatch over all of the models and bin them into a sparse grid, right? Each thread gets a model. I use the word thread, but obviously it's GPU, SIMD unit thingy. But yeah, each thread gets the model. And sort of atomic sort of, right, so what you're going to do then is you're going to find, so we just want to bin it into, we don't want to care about tunneling down and doing this. The tunneling down will be done afterwards. So we'll just bin them in this big top level. And Atomic adds them into the top level sparse grid. And if it doesn't have a model in it yet, right, it needs to allocate one, I guess. Or should we just have them all pre-allocated? Yeah, no, I think they'll all be pre-allocated. And let's say you get maybe, there'll be some maximum of how many models per area. Yeah, sounds good, doesn't it? That way there's no contention other than the atomic add. I think that's a good idea. Hey there, King, how's it going? Good to see you. Yeah, things going good, man. We've just been going over all the different sort of plans with the how we're going to build our acceleration structure, or what acceleration structure we're going to use for our spheres for ray tracing. And it's going to be compatible with lights and shadows, and we went over that we're going to be using a bounding volume hierarchy, but we're just talking about how we're going to build one of those efficiently. And it's going to be a sort of a custom way we're going to do it. So we atomically add them. But yeah, how's things going with you? You been up to much today, yesterday? Each thread gets a model, and Atomic adds them into top level sparse grid. Okay, so I guess we're going to say maybe 1. We'll say like, or 0, right? I pre-allocate sparse grid. So we pre-allocate a sparse grid with n models. Sparse grid level 0. Top level with n models. So I guess it won't really be a sparse grid. But the sparseness will be for the spheres, not for the models. It's kind of a separate grid. So it's pre-allocate a grid with n models that sort of resembles the sparse grid's top level. So pre-allocate grid with n models per cell. That's good. That sounds like a good plan. So that means then we can just bin all of those, and the only bit of contention is the atomic adds. So if you have 1,000 models, yeah. So let's just go to step 2. We can take iterations over this. So step 2 is we now have our models in each of these guys, a list of them, a lovely list. So you got a bounding box of that, and you just see which ones it goes in. Bearing in mind, it can actually go into 2, right? So it could actually go into 2. That's fair play. It can actually go into 4 or 8 or maybe more, right? If it goes there, it's going into 8. It's not good, but it's going to 8. But you're sort of doing that sort of slow thing on a low number of instances, right? I guess you say model instances, just to make it a little bit more clear. So the next one is we're going to dispatch over each grid cell. So you're going to dispatch over each grid cell. Okay, dispatch. Each thread group is a grid cell. So that means all the threads that are working together in lockstep will be operating on in the same cell. So you won't have to do any atomics. Well, hopefully in lockstep. I think we'll make them be the same size as a wave. Then we'll say each thread is a sort of a model instance, right? No. So what we want to do is bin out all of the spheres. So you probably want to... So do you want to... So the way the previous thing worked is it would go over all the models, atomic add. Then it would go over all of the... and bin the models clusters out. So I don't know the kind of architecture. Like, are we going to be having clusters? Like, because what's the point of clusters in standard sort of triangular meshes? Isn't the point so you can sort of like just render the clusters, isn't it? Right. Whereas if we're just having a list of spheres, like I don't know, maybe when you animate, it might need something. But yeah, I think we're thinking a bit too early for that. So putting in clusters seems pointless because they're not really solving a problem. So let's not. So we'll say all the is a model's sphere. So we'll do like 32 spheres of the model, and we'll just go over all of them. Wait a minute, is that even possible? Because you've got to dispatch correctly. So the problem is each model has a different number of spheres. So it's nice that you get to go in the grid cell, but if you're going over all this, So you could count the number of spheres in this stage, and then you could do a dispatch indirect. Well, not even indirect. Oh yeah, indirect. So count. So atomic add the total number of spheres in a grid cell. So if you did the total number of spheres, it means you've got to do a dispatch indirect per top level grid cell. And it could be quite a lot of dispatch indirects that you're calling. Yeah, so it could be quite a big. So you could do a custom number of dispatch indirects. So I guess it can't be that bad. They won't have any synchronization code in between them. So in this example here, we've got 4 by 4, and you did a third dimension 4, so 64 of them, right? What happens if we had 8? 8 by 8 by 8, is that 5? Is that 512, isn't it? Oh no, it's 4096. See, it starts getting a bit crazy. Wait, is that right? Yeah, I was way off on that one. That's a lot. That's a lot of dispatches right in that command buffer. Like dispatching directs in that command buffer. Um, it's kind of nice though. Kind of nice. Um, could we just do one big dispatch? Um, so if you take the total number of spheres per cell, you could probably get the number of. So you want to try and lock. What you want to try and lock is. Yeah, but locking 32 threads when you've probably got like a whole bunch of compute units is not good for a 4x4x4. You have a lot of over. Um, hmm. Yeah, you might have one of them which takes far longer and you just be waiting on it to finish. But it might be better than the atomic ads. Anyway. Um. Hmm. So each thread group is a grid cell. So could we do it where it's not a grid cell, but you could also not have to do any atomic ads? You can sort of own a region of space. I don't think you can. So we did one big dispatch. Say if you have the total number of spheres for every cell, you do one big dispatch. Um, um, so the basic idea of this one is it's going to bin the spheres into thing is though, you're still going to have 32 threads. Yeah. Right, 2 seconds. Let me have a think about this. I'm just going to go and get another drink. And I'll probably come back refreshed. And I probably have an idea. Right. So enjoy the tunes. Baby. Welcome back, everybody. I acquired a new drink. It's also quite thirsty as well, so got rid of that. Right, so back to the planning. So we want to try and effectively bin a whole bunch of spheres into this sort of sparse grid and try and avoid atomic rights. So we want to try and figure out a way where we can minimize the number of atomic rights and just bin them into a hierarchy more easily. So we're trying to dispatch all models, and we're going to do some atomic rights into the top level sparse grid. So the green area. Do some atomic adds there and work out the total number of spheres for each cell. So what are we trying to do next? There's two approaches we could take. We could try and go over the ones which have something. Right, this one has something, this one has something, this one has something. And we can be like basically get the next try and bin them into the next layer down or something. Try and bin them into the next one down. Where it makes sense. So obviously this one doesn't make any sense, but I've shown it to do that anyway. But anyway, ignore that one. This one, yeah, this one here. Put it in those 4 cells. This one, put it in this one cell. And then you'll be like, yeah, and then maybe you do another dispatch which does the level 3s. So maybe that's a way we could think about it. Let's have a think. Hey, not so red. How you doing? Not bad, not bad. Doing pretty good. Pretty had a tiring past couple of days. Just been tracing down some bugs at work. You know, you're just sort of going crazy trying to find the problem. Meanwhile, fixing other problems at the same time. But yeah, it's been alright. I'm hoping to finish up on these bugs. But yeah, it's going good. How's things been with you? How's the new job doing? But yeah, we're just working on some. We're trying to construct a BVH right now, bounding volume hierarchy. So we're using a sparse grid to sort of get things together, and then we're trying to build a BVH from that, really. But yeah, things are good. Just got home. Nice. Is that a bit late for you getting home? Oh, have the clocks changed now? You're gonna fetch something for dinner as well? What sort of food you got? If it's not too much to explain, because I am a nub, when you're doing atomic right, what are you doing exactly? Adding something to a list. Yeah, exactly. So essentially we've got like a maximum number of like 32 models per cell, and we have a little number which keeps track. So your 32 is the capacity, and then you've got a little number which goes how many are actually in there. So you go, oh, 0, and then you atomic add. When you atomic increment that integer, you're just essentially allocating a slot. You'll get a unique index back across all the threads, which you kind of want to. It's a nice feature, but you kind of want to avoid doing that when multiple threads are going to write to the same memory location, the same atomic integer, which can be avoidable, but when it's this sort of problem, it's not really avoidable because you've just got a whole bunch of data and you don't have it grouped already. Unfortunately, is that making any sense there, Catpain? So could you do something like each thread has its own list? it adds to, from that list, that thread adds all the elements to the atomic. That way, it kind of adds them up, out competing or whatever. Right, so instead I could do it where each thread has a list of where it wants it to go. Right? Yeah, I'm not sure that makes too much. Where it wants it to go, then adds all the elements to the atomic. Yeah, so basically what you could do is you could be like, there is some optimization where you could be like, I am adding 2 models to this box. And you could keep note of how many models. This is probably good optimization. You keep note of like, oh, I've got 2 models that go into the same box. So instead of saying atomic add 1, I will just keep note of like, oh, 2 things go in the same box, and I'll add them there later. Then at the end, I've like, oh, I've got 2 of these in this box. And so I atomic add 2. And then I've got 2 slots back, and then I can put them in there. So that's an optimization, but you have to do it afterwards to see how much of a win you actually get. It does complexify the code a bit though. And you have to use some LDS storage probably to store the data. Maybe not LDS. Yeah, so you have to... No, the thing is you can't do it in multiple... Yeah, you can't do it in multiple threads. Yeah, I think the way you're suggesting it, you can't quite do it that way. Because that's the whole point. That's the reason why we're trying to build that list. And that's why we're atomic adding into a list. That's the list we're trying to build. But you can build a list locally for your thread. Oh, I think what you're saying is maybe each cell goes over every single model. That's another way to do it, but the problem is you're going over all of the models. But you won't be using atomics. So if you have a smaller... Yeah, that's the way we do it for the UI actually. But I don't know how good of an idea it is to do it that way. Yeah, that's the other way to do it. But you're going over the same models on multiple threads at different times. So you're basically doing number of cells times number of models complexity. As opposed to just number of models, right? That just look over the ones they need to put it in. So there's that. Right, so if we have this if we have this where we're going to essentially go down one more level for all of the ones which actually have some model in it, and it can put the spheres no, because if you did one at a time so we could just drop them all. So if you have like a model in here, you could be like, oh yeah, just drop all your spheres into this thing. But then I think we wanted to have per cell in the sparse grid, we wanted to have a maximum of maybe, I don't know, 8 or something. Just a number. So if we put it all into the top level cell, it's going to overflow really quick. Unless you did something else while you're building it. So you might as well refine all the way down to the lowest and drop it in there, I think. Okay, so we'll go with that approach still. So the question is though, is about how do you do it without the atomics? Now you've got the models in the bins, right? What did I do in this previous thing? What was the problem again? The problem is with dispatching over, so each thread gets a sphere. Yeah, we didn't know how many spheres, so we would have probably had to do an atomic indirect per. Yeah, right, so let's read how this one did it, and we'll see if this one has the same problem. Do the atomic out of the ABB. Max number of clusters. This did clusters, but I don't think we're going to do clusters for models anymore. Dispatch of each thread group is in a grid cell. Dispatch over all grid cells. Go over all clusters. Yeah, but the clusters, yeah, this one has the same problem. Yep, same problem. So the spheres do clusters. Yeah, so you have to have, you either have to pick the maximum number of spheres that each cell has and run that for all of them. And a model doesn't uniquely go into a cell. If a model uniquely went into a cell, no, it's not true, is it? No, I tell a lie. Tell a lie. So we need to what do we need to have? So thread. So, okay, so let's just say if we could magically, a thread could go in, you could have 32 threads in here, and you would go over every sphere inside a model and basically refine it down and put it into the lowest one. So you still have the same problem where you got to like allocate and fight within your so you got 32 threads going in lockstep, and you get your sphere, and you go, well, it's small enough to go all the way down to level, to the lowest level BVH, or lowest level sparse grid thing. So you'd have to sort of refine. So you'll be like requesting that this blue one is allocated, and if another one's trying to do it, yeah. So I'm not sure how you'd do that. You'd probably want to use wave intrinsics to sort of say. I think there's ways you can do it. I'm just not familiar with the exact wave intrinsic I would use. You want to, because you could have 32 threads, right? A few of them want this one to be allocated, and a few of them want this one to be allocated, right? So it can put a sphere in there, and it's not allocated yet. So you need it to be allocated. So maybe we do the similar approach where we just go sod it. Just pre-allocate all of them, and we'll get rid of them later. But then that's... Yeah, I'm not sure about that, because then you're just going to keep them. You can still do it with atomic compare and swap. If I think I get what you're saying, and that's not pretty. Yes, you could do the compare and, I guess, to compare and swap like a lock. Yeah, it's not good, but I think you could do. There's a few intrinsics. There's ballot, right? Wave ballot. I'm not familiar with this one. I know it's like a way to vote, so I just want to see. So you got like, you can obviously XOR or and all that, like you can have a bunch of flags. So you could do what does this one do? Returns a Unit 64 of a bit mask of evaluation of Boolean of all active lanes in the current wave. So that's the point up to 256, basically. Waves. But you only use the first integer, because you only use 32 threads, right? Inside a current wave as well. All active lanes. Okay, so just active. Oh, no, sorry, no. Yeah, so it's basically just an XOR. A wave active OR, sorry. That's what I meant. Just wave active OR. And count bits. But with your current wave index as a... Yeah, but with your wave index. So it's waved in the wave index and OR at the same time. Okay. Right, so that one probably won't help. Yeah, I guess you could probably have a bit set. We're like, okay, which ones do we want to allocate? And we iterate over that bit set and allocate them. You'll get 3 threads. Say you have 3. Yeah, there's ways to wave intrinsics. You'd be like, oh, 2 threads want to do this one, 2 threads want to do that one. You basically OR using wave active OR into a bit set of 32. Maybe you have it depends how many cells you have. So you need a bit set for every cell, and you basically then do a least set bit type of deal and iterate over all the bits. Yeah, you count the number of bits, and you could probably get each thread, and just ignore. You could get, say if you have like 4 of them, 4 of your threads could do the allocation while the other 28 just do nothing. And then you can put them in, you can do the adds, but then you got to do another atomic add, right? But it's local. It's not really atomic add, it'll be a wave. It's kind of an atomic add, but within your wave. Yeah, it's within your wave though. So it'll be faster. Because it might not go out to main memory. Or will it? Yeah, I'm not sure how you could guarantee that with functions. I'm not sure, could you guarantee that with the atomics? You can do it into LDS, and then that's basically an L1. And that might be the optimization, you do it in LDS. Do your atomics into LDS, and then write the main thing out into main memory. Yeah, I think that's the way around it. So I think it's possible. So if we can get something like this, it's possible to achieve something using maybe not it wasn't ballot, but yeah, wave active or something. Yeah, bit or. You could do like a bunch of these guys. Hopefully not too many, because I'm not sure how. This one's probably not that bad. But yeah, something like that. And then you could probably do the allocation, and then do the do the atomic into LDS memory, which would be cheaper. Or maybe not even LDS memory. Yeah, maybe static memory. That might be cheaper. Or it should be cheaper, then write out to main memory after. Yeah, that sounds like a good idea. I think that'd be a good approach. So now we've just got to figure out how we can lock. So that's if we use wave intrinsics. And then it kind of suffers from the same problem where where so if you have tons of sparse, you have tons of these sort of sparse cells, you want to do a dispatch indirect, and say if you have 8 by 8 by 8, that's 4096 dispatch indirects, which is not ideal to be recording into a command buffer. So it comes back to that same problem again. And if you have a smaller number, you kind of want to have as many as you have compute units, maybe. Or somewhere near it, because otherwise you can have idle compute units. And also, if some will take longer than others, and if you have a very long, one with like 20 models and the rest have no models, then it will take a longer time. But then again, it's a sparse grid, and not everything's going to be filled anyway. Okay. But you have to dispatch indirect anyway. Why has my game been running? Just burning electricity. Okay. Wait, what am I doing? I'm in the wrong one. This one. Okay. So could you change the thread group? So your thread group maybe covers multiple cells. It could just go over for all of the cells I am doing. If you have to go over all the spheres in your cell, basically. I think that's the biggest problem with this solution. Yeah, so maybe... Oh, no. Right, so you have a dispatch indirect. And then you have your thread group. And you launch in n groups. N where n is the number of spheres. Yes. Okay, I think that's the way we can do it. So the other way we can do it is you could probably have a maximum number of dispatches that you want to do. Maybe there's 8, maybe there's 16. But the idea is each thread group is going to be a range of cells. Is a range of grid cells. Each thread gets a model sphere. So we can do a dispatch indirect. Yeah, I think this is the way we can do it. So rather than owning one, we'll own multiple. And we'll simply just do one at a time. So we'll go over and do all of these guys, go over and do all of those guys, go over and do all of those guys, then do all these guys. Bearing in mind, you're going to have... So you'd pick the right number. So I guess when we're doing this, we need to fill in the dispatch. There might be a... Where are we filling this with dispatch indirect, isn't it? Yeah, I think that's what we'll do. So where we're going to fill in the indirect arc, so you've got the number of total spheres per grid cell, right? And you'd have a bit set of all of the cells which have spheres in them, or sorry, models in them that you're going to break down into spheres. And so I guess you could be kind of intelligent and sort of um, yeah, because if you did a dispatch over all your groups, over all your cells, yes, that solves the problem of having just too many dispatch indirects that you're calling. You have a fixed size, yep. So that way the grid could be any size really. Just got to fill them in. See, I guess you could do a pass where you do a sorting, and you sort of wait. You sort of wait. You know, like this one might get like these four, or whatever. And you want to make sure that something gets another four or something. Maybe this one gets this four for some reason. I don't know. Maybe it's got a little sphere in it or whatever. That the total number of spheres that are sort of given to these dispatches is about the same, so they will last as long, right? Yeah. So for each thread group is a range of cells. Is that right? Breaking this groups divided by spheres number. Yeah, I guess so. Something like that, yeah. So I just want to double check this is all right. So you're doing, because it's a bit confusing with this thread group stuff and threads sometimes. So if we were to launch a compute shader, full screen for instance, and you have like tiles of 16 by 16, so it's 16 threads per yeah 16 threads per group, and then you launch n groups to cover the whole screen, right? They'll be running at the same time. So I don't know if this is guaranteeing us anything. Yeah, because they'll be running at the same time actually. Shoot. Uh, hmm. Because you're trying to dispatch in a thread group. Like, yeah, ideally only doing. Right, see, we kind of want is like each wave. If each wave, and yeah, I think that's the thing. Each wave gets a group. That's the thing I wanted. Yeah, that's what I was thinking about. Yeah, maybe we'll communicate over LDS. Maybe that'd be better. Ah, Manadono, thank you so much for the raid. Appreciate it, sir. How's it going? How's the stream go? Welcome, raiders. How's things going? We're making we're trying to figure out how we're going to construct a BVH on the GPU with all the threads. Yes, kind of a bit of a tough one. I'm hoping to. I think we're close though to just finding that final thing. So where's an example code? Yeah, if anyone has any questions, feel free to ask, and we'll go over we're doing a little bit. So for instance, let's go to like that clear shader. It's a good example, right? You're doing 8 by 8. So then you're launching enough. So locally, you're doing like 8 by 8. Bearing in mind a wave is 32, so there's actually 2 waves going. And then you're launching them across n. Right. So really, we want a thread group. Maybe it is right. We want a thread group to own. We want a thread group to own. So maybe we do like, let's do a big old number like 256 or whatever. Because you want to churn through like tons of spheres in a model. Maybe a better number is 128. Right. So you're saying definitely launch this. Maybe it's a bit too many. So you're saying like launch this many threads, my local group, and my thread group gets a one of these. That's not a good idea. So let's see if we can do it from this approach. Because if you could do it each, then you just launch one. Then you do one dispatch. Is that right? No, it's not right, is it? Yeah, this is quite a difficult problem because you have 2, 5. Yeah, okay. So you can't do it with thread groups where each group gets a tile. Because if each group gets a tile, you've got to encode. Because with a thread group, you basically can have LDS, right? Some local data storage where you can share between all the compute units which are not running in lockstep. And you can sort of synchronize between them as well and tell them all to wait here until they all get to this point. So theoretically, you could do something smart there. But nah, I don't think it can work. I don't think it works out. Yes, tough. It's a tough one. Can I explain the problem? So we're just currently we've got this sparse grid. We're currently thinking about binning, like we're just trying to think of essentially building a BVH. 3 levels, maximum of 3 levels. And so it's a maximum of 3 levels. And the way we're thinking about building it is by building a sparse grid. And we're essentially binning a bunch of spheres into this sparse grid and trying to sort of construct a BVH from this grid. So the current issue we're facing is we're trying to find some optimal way to bin. So we've currently binned a model into sort of the top level, and then we're trying to find a way to sort of break the spheres down into the sort of lower levels of the sparse grid. But I'm not sure if it's possible. If that makes any sense. We're trying to find a way to sort of iterate over all the spheres, and kind of lock regions to certain thread groups or something, but I don't think it's... Hmm. Yes, I don't think we can use LDS because LDS is specifically for a thread group and it's fixed sized. And you have to compile it in as well. Right. So maybe no dispatch indirect. So if we make a thread group 32, so it matches a wave, then that problem is that you basically see this is where you need that new DirectX API. I'm not sure if you guys know this one, but there's that new. This is a type of problem with that new DirectX DX12 work graph. So this thing allows you essentially like dispatches, like indirectly dispatches on the GPU, and this is the type of problem we're having. We want to basically tell the GPU to do dispatches from the GPU. It's kind of a little bit complicated reading this, but yeah, this is the type of thing where it's like if we had this in Vulkan, it would probably be something we would use, but we don't have that. So is there a way around it? Yeah, DX12 work graphs. My days. So yeah, we're going to the problem of, we have a whole bunch of, we can launch across all spheres in a model. And just bin those. The problem is the model doesn't, hmm. So what happens if we went over all of the spheres? Could there be a way? He's in the atomic add thing again, isn't it? It's not going to be a good way to do it. Get this thing up. Hmm. Mm-hmm. Yes, the only way I can think about doing it is dispatching over all spheres. So I guess should we explore that method and see if there's any way we can speed it up? Because the only way I think about doing it, if you dispatch all spheres, you're going to have to do an atomic add, right, to get it into... Yes, complete nightmare. We could probably tackle it from the model's perspective, right? Maybe that's another way of doing it. So you have a model, and each... Man, it'd be really nice to have that work graph API. Coming to Vulkan 2. We need it now. Oh, it is. There's a beta header. Let's go. And a beta kernel driver. Boy. Yeah, the problem is it's only limited to AMD hardware or whatever. And it's specifically an AMD extension. Ugh, horrendous. Yeah, if only, eh? If only. Yeah. So the ray tracing API initially was for NVIDIA, and then they made it a proper one. So maybe, or a proper one extension for multiple vendors. They did some slight changes, so they might do the same thing for that then. So could we think about this from a model's perspective, right? A model. Could you build a local? Could you build a local sparse grid per model in the scene? Well, you need a dispatch per model instance from the CPU, which then would add up. You know, if you have 1,000, it's 1,000 dispatches. So you have the problem of knowing the total number of spheres. So would the clusters, would the clusters sort of, so if we added model clusters, right, this is where it could help. If the model had clusters, could you just dispatch over every cluster and do something with that? Because it's a smaller unit. And the clusters could say have a maximum size of 256 spheres per cluster. And what you'll do then, so you could do a thread group of 256, right? So with a thread group of 256, could you do anything with that? You could then use LDS memory to then be like, I want to go to this. I want to be binned into this part of the grid, right? And maybe you can have a coordinate. You'd be like, well, I want to go here. And you can work out the exact place, even if it's sparse. You can work out a 3-layer coordinate. You could be like, I want to go in this grid, right? Down into that grid. So it's like a 2. You want to go down 2 levels and go there. And you can build up a local LDS sort of storage of like which cells you want to go in or something, but then you have to sort it. And then you could do your atomic adds and maybe make the grid with like one thread instead of like loads of threads, right? At the end. And then you would alleviate a lot of the atomic operations that overlap, right? A lot of the locking, you would minimize it. So I think that's some route we can take. So I think we should explore that one again in a little bit more detail. No one ever manages to get the base API complete. Yeah. Oh, hey there, Sully. How's it going? Good afternoon. Good evening. whatever time zone you're in. Yeah, with Vulkan, it's kind of got a good thing where they have they bring extensions into the core with like a new Vulkan release, but they haven't had a Vulkan release for I forgot how many, maybe 2 years now. I'm not sure. But every time they do that new core thing, it's really good because they brought a lot of stuff into the core that were extensions. And basically, all devices have to support it for the most part. So it's really handy when they do that. Right, so we break stuff down into clusters. So when you build your model, so you make your model in the editor or whatever, and we just break stuff into 2, 5. Like we're gonna have them in grids anyway, right? They'll be placed down into a grid. So we should be able to group them by 2, 5, 6, or whatever the cluster size is, and build these clusters. And there'll be wastage on obviously these small clusters, right? And we'll just group it. Group spheres. It doesn't really matter how we do it. So if we have that unit of grouped spheres, we can use that unit of grouped spheres and just say, hey, where are you going? Turns out, grouped spheres are next to each other, which means they're likely going to go into the same place, right? But there's another problem. Grouped spheres are also going to end up going into multiple cells, right? So at most, a sphere can go into maybe, we could give it a limit of saying 8. We can give it a limit and say, at most a sphere goes into 8 possible cells. It could actually be more though, but let's just say 8. So with that, we can then build up an internal list in LDS memory where we keep track of all of the places where we can insert a sphere. So what might this list look like? So you're probably going to belong to the same sparse, well, you're not really. Yes, you need essentially like a 3D coordinate into this sparse grid because there's 3 tiers, right? There's only 3 tiers at most. So you have a 3D coordinate, and you have a sphere index. And you basically want to say, you want to keep track of the number of spheres you want to keep track of the number of spheres inside that grid cell, inside that grid 3D coordinate for the grid cell. So then when you're at the end of your compute unit, when you're at the end of your group, your cluster, you can then go over that list and do the atomic adds and get the allocations and then filter them into the right places. And that way you're doing an atomic add, rather than doing an atomic add per sphere, you're doing an atomic add per tile where multiple spheres could be going. And they're more likely to be going into the same place. Right, so I think that's a good solution because it's sort of local to the place and it reduces the number of spheres, and it seems possible to dispatch easily because you just count the number of clusters, right? So is it worth doing this model instance binning anymore? Like, because you just need to go over all the clusters, right? So we just need a pass that counts all of the clusters. Or not even a pass. We just dispatch over all clusters. So, okay. Plan, restart. 1, dispatch over all model clusters. And Right, so we want to preface this with model equal array of clusters, cluster equals 256 spheres. Now, is 256 a good number? If we're thinking about having tons of, it all depends about the LDS memory. That's what it, so AMD RDNA 2, because that's what I've got, LDS size. So LDS is local data storage. You have it per thread group. Right, so we'll do some maths with an S. Multiple maths. Multiple math. So workgroup processor has 128K LDS. Okay. So that's shared across. I got to get this right. LDS. Local data store. Booyah. GPRs and LDS. It might be here. No, that's probably in the allocation. Where's the local data store again? So the problem is a workgroup processor can actually switch between, it can preemptively, is that the right word? It can switch between, it does a texture load and it's like, crap, I'm going to be stalling. So it'll switch out to another shader, maybe the same shader, but for a different set of data. So when you have LDS memory allocated for a shader invocation, you've actually got to have it for the other ones as well. And this is a similar thing for the VGPRs, the vector general purpose registers. So we just want to quickly double check the number. And I guess I'm going to not account for my Intel one here. But maybe the cluster size. Yeah, maybe we do the clustering at boot on the machine or something. Like when you got a model, we cluster it. Yeah, maybe we do the clustering locally, depending on the hardware or something. 128 each workgroup processor, right? So what you have is a workgroup processor which actually has two 32. So there's two 32 SIMD units, which you can sort of think of as threads, but not really threads. It's just able to do 32 wide multipliers at the same time, right? So they can also go in lockstep. So AMD hardware has the option of doing 32 in lockstep and making these run different shaders, or it can make them run the same shader and do 64 in lockstep. It's kind of cool. So it has LDS, local data storage is shared between it's just shared between the workgroup processors. So if each workgroup processor has 128K, you got to be careful. I think it supports up to 10 there's a scheduling thing where it's sort of like how many need to find it. 10 something. Haven't gone too far. How many compute shaders can run on these workgroup processors? I think it's on the workgroup processor. Or CUs. A single workgroup may allocate up to much as 64K LDS memory. That's fine. Okay, so each one of these gets 64. So technically there's 64. Right, so yeah, 64k is the number. Maybe, depending on what we got. So workgroup processor. Where's the bugger I'm looking for? We want to know the number of shaders it can run in a unit. Oh, wait. I thought I had the name. The name to look for it's scheduler. No, it's not scheduler. Controller. That's it. I remember seeing it. Here we go. Right, it's got to find it. Not memory control. It's maybe in another document. Okay, it's fine. It's not far. But yeah, there's like a wavefront controller or something. It's not any of these. Fine. The next document. So this is the RDNA document. This is it. This is it. Right. So this is RDNA, not RDNA2, but I think it's the same thing. So they have this wave controllers. So basically per compute unit, it stores. Each SIMD has a separate instruction pointer and 20 entry wavefront controller for a total of 80 wavefronts per dual compute unit. Wavefronts can be from different workgroup or kernel. Oh, sorry, for a different workgroup or kernel, although the dual compute unit remains 32 workgroups simultaneously. Right, let me reread that again just to understand exactly what the numbers, right? Fetched instructions are deposited into wavefront controllers. Each SIMD, so compute unit, has a separate instruction pointer and a 20 wavefront controller, 20 entry wavefront controller, with a total of 80 wavefronts per dual compute unit. That's the bit I don't get. Was that the old? Is this GCN it's describing? No, GCN is four. Yeah, so I'm confused by that number because I thought it was only one per. Right. So anyway, wavefronts can be from different work group kernels. So kernel mini compute shader. Not sure what it means by work group. Oh, have a good night, so Red. Good night, Red One. Have a good rest of your work week, my friend. I'll see you potentially Thursday. Although a dual compute unit contains 32 work groups. The new waving controllers can operate with 32. Right. Not quite overshoot it, but I think it's 20. I think it's 20. Wavefront controller. Yes, I'm not sure how many. So I think it's 20 basically. It might be 10. The 20 entry. Yeah, it basically highs latency that way. So say we use the number 10 to be conservative, I guess. So we've got 64. So one compute unit has 64K of um, LDS memory. So you're dividing that. Wait, 10 was conservative, right? Actually, it would be 20 is conservative. So that's about 3.2K of LDS memory per cluster. Okay, so this is a number we can work with. So let's just say we've got about 3.2K to work with in a cluster. So let's just write this number down. Where's our little... All right. So we've got about 3K per cluster. So we have 256. We need like a little strut. Maybe we can do a U32 per sort of per thing you need to bin, and there's possible for 8 of those, right? Because it's possible 8 places where it could be binned. That's what we're going to max allocate for, I think. That should be enough. So a sphere could be overlapping. It could be overlapping at most, right? Been a bit. It could technically be more, but on average at most, I think. 8, right? Obviously it's 3D. Different cells. So we want to have essentially this 32-bit integer is going to have this sort of type def U32 bin binned sphere, something like that. So this is going to be strut binned sphere. We'll do like let's do it this way. It's easier. So say U32. You'll have like a 3D coordinate type of thing. So you have level 0. I'm not sure how many bits you need, but is there enough? Is there enough bits? So 4x4x4 is 64. So you need quite a few bits actually. 6. So 8 is 3, 16, 32, 64. Yeah. My man. So 1. So say we support up to something like that. So that's 24 bits already. And then you need like a sphere index inside your cluster. But you have like 256 in your cluster, right? So it might not work. So you might need 2 U32s to really make if 4x4x4 is not enough. Right, anyway. So yeah, I think we'll do like a binned sphere. We'll make it a U64. There's 2 32s. And you can just do you divide that into 3, so like 10 10. And maybe the lowest, maybe get more in the highest, something like that. I don't know. Whatever. And then you just do sphere index with 32 bits. It's just a bit big. But let's just run the numbers. So imagine if you have this bin sphere and you want to support up to, so you have 3K LDS per cluster. I'm going to do 8 slots per sphere. So it's 256 times, that's the cluster number. So I guess we'll say cluster sphere count. Let's just say that's 256. And then let's say we've got a number of, what was the other one? times that by the max number of max sphere location, max slots, whatever, for single sphere. Could probably do a much better name there, but let's just say there's 8. So essentially you want to have an array of this in LDS memory of this number times this number. So, right, times by 8 bytes. So let's run these through the calculator. Just to be absolutely sure what the number is, times by 8 times by 8. Oh, that's a big number. So clearly times in by 8 for it being that is too generous. Yeah, it's a lot of bytes. So we divide by 8. Oh no, that went way too much. Sorry, 256 times 8 times 8. Okay, 16k. Clearly a bit too much, but if I divide it by the 8, it fits. Right, so it fits into that LDS thing. See, I have to really get a good number. But maybe that's enough. Maybe that's just... So... Yeah. Right. I'll be right back. Just need to get another drink, and then we'll think about this a little bit more. Thank you. Right, welcome back everybody. So I think we're onto something here with this. The only problem I'm seeing though is different lots will probably want a smaller cluster size. Maybe? No, I guess you'll just cover the whole, the whole model. Well, no, you would need, I guess if you're doing lot 0 or whatever it is, the one with only one sphere, you would just won't use this clustering system. This cluster binning, you would just launch the single sphere, something like that. Yeah, there's definitely edge cases, but I think they're solvable. They're pretty solvable. So you might want different cluster sizes. So we might need to repeat this shader for different cluster sizes, depending on hardware. Because you might want a smaller LDS memory to use up. But this times by 8 here is too much. So my thinking is So you're not going to bin. Can we get away with binning a sphere in one location? Wait a minute. We're making a bounding volume hierarchy, right? Which means you only want it in one BVH anyway. So you probably only want to bin it into a single box and just group it in. Yeah, I think that works. Yes. So the BVHs can overlap. The BVH things can overlap, but you only want... Yes, that works. So that means this LDS thing should be fine. Is that Froxel space? Yes, you see Froxels. Yeah, we're going to be doing Froxels for the clustered lighting. But I was thinking about binning spheres in there, but it's not been a good idea. Because you won't get the... you don't handle off-screen. You know, you have a light off-screen shooting. You do a shadow map, and it just doesn't... Or whatever you're doing, shooting rays, and it won't get the sphere off-screen. So we're doing a BVH now for the spheres. We're just trying to find some optimized way of processing spheres and binning them, really. But I think we're onto something there. But how's it going, really much? How you been? So I think this is a decent idea. We only need one location per sphere, and we can keep track of the location. So the thing is, though, is can we get away with doing 32 bits? Thank you very much. Well, yeah, it's going all right. It's going all right. Like we've taken some directions where we're like, oh, it's not quite where we want to go. But yeah, I'm hoping this is gonna be speedy enough, and not too complicated at the same time. I'm getting crushed by work, losing my desire to do tech. No. Oh, tell me. Oh man, I remember having the same sort of feelings before when I had my previous job. How am I doing on camera? Okay, it's cool. Well, my head was half off. Yeah, yeah, I've been there, man. It just made me want to sort of be like, can I live out in the wilderness and just, you know, have my own, just sort of like live off the land and just, you know, get out of society. I remember having that experience. Yeah. Well, if you could focus on finding a job that you enjoy more, I recommend doing that. Obviously, it's a very hard thing. Yeah, I remember I was going through that. It was really tough. I ended up quitting and then looking for a job, and that was kind of hard. It was a lot harder actually. So try and keep it if you can. Just move into management and make you miss tech a lot more. That's cool, man. That's cool. But yeah, if you want to chat anytime, feel free to send me a message um, on Discord and that. Yeah, yeah. Touch. Yeah, you go and have a run, touch some grass. You know, that's it. Yeah, yeah. Definitely do more of that as well. There we go. Yeah, as soon as you leave a job, you've got to explain yourself why you left a job. And if you didn't have a good reason, you got to lie. And if you're not good at lying, well, it'd be harder to get a job. Yeah, man, I can imagine. Yeah, like it's a big thing to communicate well. when you're working with other people, that's for sure. Right, can we reduce this sphere index? So 256, you need 8 bits. I just need 8 bits, right, for that cluster. To just index a sphere in a cluster. Oh, 3D coordinate. You will get a lot more bang for your buck if it's a 1D coordinate that you then later turn into a 3D coordinate. So how is it 3D when it's going through L1, L2, and L3? Right? So theoretically, we could probably just treat it as a, you know, you got this cell here. L1, L2, L3. Oh, yeah, you could probably say you probably need. You could probably do the lowest level. Yes, you might need. So you probably want to dress these in the first. You know, the top level in the first n for the number of cells, bits, space. Then imagine you have this whole blue grid filling the whole place. You're addressing that, and then you're doing the whole other grid. So you probably modular. There's quite a lot of modular operations though. Maybe. There's probably some takeaways, and then some modulars 3D, flattening a 3D chord. I didn't realize you could do that button. Okay. Yeah, I think that'd be a good idea. Hilbert space. I'm not sure what that is. What's a Hilbert index? But yeah, you can like flatten it basically. I didn't realize someone named it after themselves. Is this plain C? I've been wanting to try my hand at Vulkan, but everything is C++. Yeah, this is all pure C. We also have our own C to Spear V compiler. So we actually have our shaders written in C. Obviously, it's a subset of C, right? But, you know, and it has some extensions like swizzling. But yeah, it's all in C. We can share structures and functions and stuff. So, yeah, it's all written in C. Everything. Hilbert space. Prepare to maths. Oh, it is. Is it inner product that is complete with respect to the norm, the outer product? Right. XY or X12. I'm not sure what that is. Yeah, they tried the Froxel thing. Yeah, that's one of his experiments, and they had similar same problem we just thought of, or I remembered basically from that probably, is you only get screen space lighting if you bin your spheres in Froxel space. Obviously, your lights get binned fine because you're binning the area that the light actually affects. So outside of them is fine. You know, going outside is fine. But if you have a sphere outside isn't bin inside a Froxel, yeah, that's the problem. Quantum mechanics, yeah, that's not not helping explaining it. But yeah, I think there's a way to look at it to do it. But basically, we should be able to compress it into. So if we just join the remaining bits. There's 24 bits, right? Well, I think we should be able to do it. 24 bits. Essentially, this would be a level, a sort of a slot index, or leveled slot index. Something like that. 24 bits, big number, it's about 16K. Hilbert curve instead. Oh, okay, you meant space as in, yeah, as in like a transform space. Gotcha. Gotcha. Whoa. That looks cool. Huh. There's a for loop. So it converts it X, Y. Oh, interesting. Yeah, that might be quite... I'm not sure what N is. N by N is number of cells. Right, it's interesting. I'll look into that. It looks cool, though. Wee. It kind of reminds me of like a Morton curve in a way. Kind of reminds me of like a Morton curve. More likely, yeah, interesting. Than just doing the linear thing. Yeah, but I don't know if caching's the problem. We're just trying to flatten an index. We just need a fast way to convert an index from flat into 3D. And it's not about data locality in this case. Or things being next to each other. Yeah, I don't think that's going to be our problem. We just want to have our... Wait a minute. Yes, it is because we're going to have to sort them. Maybe. Will we have to sort them? I don't know. Yeah, no, it definitely does help the data locality stuff. But yeah, just you just got to use it when you need it. But yeah, this will work though because it converts. Yeah, we should get 16 million. Sorry, I'll do the. Yeah, 16 million. So say if you have a 4 by 4 by 4, which is 64. That was a wrong number. So 64 plus, maybe you did a bigger one where you was like 8 times 8 times 8 for some reason. And then you did like maybe you did bigger numbers. I don't know. 256 times 256. Right. Times 256. Okay, so then you start getting into problems there. So if you had a big 256 by 256 grid, wait a minute. Yeah, then you hit that 24-bit number, which is a shame. So you have to have layers of simple. So we have to make sure that that works. It's 8 times. What is going on with this thing? 8 times 8 times 8. To say if you had like 3 of those, right, you're well within the limit. But it's okay. Right, so hopefully that's just something to, Yeah, so leveled slot index bin sphere. So you'll build up these bin spheres, that'll be an LDS. What else do you need in LDS memory then in this case? You also need a number to these bin things. You could probably sort them. If oh yeah, sorry, I forgot to mention this stuff works especially well for textures, texture caching. Yeah, I'm not sure, it won't work for buffers probably. Because for 2D textures and 3D textures, they're basically, yeah, they're next to each other in memory. So are we going to sort these bin sphere locations and then be like, or we should probably keep a number saying here's a number of spheres for that slot? No, I don't know. Yeah, do you want to sort them? So if you sorted them, it means you could do, yeah, so you'll probably sort them by this level slot index, basically. And then you probably want to go over all of these on the final thread, and then maybe there's a way to multi-thread it and sort of do the atomic adds on a single thread. Maybe you can figure out the number of unique slot indices. Maybe there's a way to do that. Yeah. I think that could be, because you don't want one thread to go over all of those bin spheres and copy them. Not ideal. Yeah, the Morton curve is easier to evaluate. It's a for loop, it's a fixed size for loop. So you can do it in like, yeah, the code is, shader tool. Yeah, here's an example of it, right? The way it fills up. So here it's a for loop of 4, and you just do some XORs and ANDs, and you can do that. So there's also a 3D one as well. So if we had a 3D, that would be quite cheap. It's cheap actually as well, isn't it? Yeah, so we should probably use the Morton curve, because then you can compress it. But I don't know, it's got more dependencies. Yeah, it's got dependent. Yeah, so maybe it might be better just doing the modulo. I'm not sure, we'll see. Just interleave bits. But yeah, something we can explore though. What do you mean by interleave bits? Exactly. We probably also need to say like what level we want to go in or something. No, we don't. So yeah, how are we going to bin these? So you have 256 threads running, so you'll have different compute units with 32 threads that run in lockstep, right? Operating on this. And you'll sort of communicate over LDS memory. This sits in LDS. You'll probably need a counter or something that sits in LDS. So there's another 4 bytes. What else? So you can basically append, you can atomic add. It's local, so it should be fine. Is that right? Yeah, atomic add-in to LDS should be cheaper. So that slot index could be like a really big number, and you probably want to find how many times you're going into the same slot. You don't want to have another array where you have the number of slots. Yeah, where you have the slots and you sort of loop over the array, and then you have another array of counts to say how many spheres go into a slot. So you could have it that way. It'll make the end a lot easier because you could probably multi-thread it. Right? If you had this information, it would make it a lot better. So num spheres per slot. So you probably have like, that's a lot. You start getting a lot more memory. Number of spheres per slot. Well, you can just join it. So you do another one where you say slot index with a slot count or spheres count. Then you could just atomic add it by 1, and because it's in the low bits, it will work, or something like that. You need to do atomics though. So you'd have to loop over that. You need like a bind, like a slots count. Unique slots. Call it a unique slot. That sounds better, right? So that is actually the same amount of memory as we looked at before. It's about 2K, 2KB, right? Plus another 4 bytes. It's not quite a square number, but you might be able to reduce this by 1, each of these, and make it 255 per cluster, and then it fits within 2K LDS. Wait, no, reduce by 2. Yeah, then it fits into 2KB LDS, which might be a better number. So to make this sort of unique slots thing, when you're binning a sphere, you've got to calculate what slot it's going to go in. So currently we've got a thread per sphere, and you're trying to put it into a slot. So you'd have to go over all of those unique slots and do a search. And you're doing that every time to see if it's in there. It's not... That's not going to be good, right? Because you fill up 256 unique slots. That's a lot of searching for a shader to do, but it's in a nice. You have to do an atomic load probably because it's shared between the thread group, all the threads in a thread group. So searching over this is going to probably be a bottleneck. You could probably do some form of hash table where you just index into it, but then sort of looking over the list at the end is so you could do another array, but then it becomes more memory, which you could use as like a hash table, where you're looking for a key, and then it's got to be like one of those multi-threaded hash tables where you do use atomics. I think there are performance optimizations. It does make code more complicated, where each wave could be like, are we all inserted into the same one, and sort of avoid contention there with all the threads. But still, it's got a search and search for a unique slot. Um, hmm. So I think there's another way. So we just need like a way to sort of quickly tell if it's not been put in there already. Um, yeah. Or we could just make the cluster size smaller, and then it becomes less of a problem. Um, if you made a cluster size 32, if you literally just made a cluster size 32, you don't need LDS anymore. So that's a lot of clusters though in a model. That'd be a lot of clusters. But maybe we can yeah, so maybe when we add a model, we can sort of clusterize it. Maybe clusterize it on the GPU or something. Have them ordered, the spheres ordered in an array, and you can sort of basically index into have a cluster index, and it's just cluster index times 32 gets you your sphere index. Then all of this could just be in local memory, right? In static memory for your invocation. Then when it comes to testing a sphere, you just use wave intrinsics. Right, you literally just use wave intrinsics to tell if it's the same slot that you're adding. And then you should be able to test 32 slots at a time. Is that right? No. Yeah, you've got to queue up. Yeah, you probably got to get all your slots together. Yes, I think this could be a better way to do it. You won't be using LDS anymore, you just have these sort of like statically instead. Binned sphere, unique slot. So every time you check a sphere, you go, well, I've got this slot index. The problem is the slot index is not the slot index is not a small number. It's a big number. So how could we yeah, it's kind of a big number. How can we, across all the waves which execute in lockstep, how can we make those make how can we make those sort of deduplicate them and also add Right, so let's look at the wave intrinsics again. HLSL wave intrinsics is just a good place to look. I do have them in mind, but I think I might be missing one or two. So Savaganda. So you can obviously read at specific lanes, so you can pass things around, but I don't think these are that fast. Yeah, so you got to be careful with wave intrinsics or not use them too much, because they can actually be quite slow. But we could shift them around. I think shifting is actually quite expensive to shift, because you imagine you've got like a register, which is like 128 wired floats, and you basically rotate them around. I don't know how fast that is, but I could have swore it wasn't that. But maybe we could iterate over all of them that way. See, wave active min will make you all get the same one, given x. You could all read through each other's lanes and just compare. That's another way to do it. Yeah, I'm not sure what is slow about them. We'll have to have a look. There's sometimes they have been much slower. I need to find. I think if we look on the RDNA document, I think there's a good way. ISA. But yeah, I think you basically. I think there's DS Swizzle. Yeah, I'm not sure about the. I think there's timings. Yeah, so Swizzle allows you to like, swap stuff around, but it all depends on how many instructions they compile to. But yeah, I'm not quite sure on the timings specifically. It always comes to the Swizzle. Yeah. But yeah, I'm not sure about the right. From what I recall, shifting isn't slow if you're not rotating on until anyway. Right. Yes, I think it was the rotating I was doing. Yeah, we could read at lane, and each thread can read at the next lane over and just wrap it. And then it could be like, are you the same as me? And then if you are the same, but how many times would you need to do that? If they all read the one next to each other, is there some way where you can sort of make them, so you've got 32 threads. The Spider-Man meme. Yeah. You point to the next one, and you read the next one. How many times do you have to go? That's an interesting thing. So let's just imagine wave 4, right? 4 SIMD unit. Beast of a machine. You know, that's SSE 128, isn't it? It's SSE basically, isn't it? The 128-bit register. So if you say you see got 4 threads running in lockstep, blah blah blah. This one reads this guy, this one reads this guy, this one reads this guy, and then this one reads this guy. So how many times do you have to do this before they've all read each other and compared? Because you're reading the one, like this one is getting compared between this one and this one, right? In one iteration, right? And that's obviously not comparing it with itself, so that's 2 times. So you only have to rotate or do the read of the, like this one hasn't gone against this one, right? So I think you do one more. So it might just be, yeah, I've already got, I don't know the number, but that means you need to rotate twice or do 2 read lanes per thread. And also if the read lane index, has that got to be constant? No. Good. It doesn't have to be constant, uniform. Right, so you could do that. So if you did, let's do this a little bit more. Let's say there's 8. So for 4 you needed 2 iterations. For 8, that one reads that one, that one reads that one, that one reads that one, and this one reads this one, right? So let's mark this out each iteration and see how many we get. So for the first iteration, this one and this one is compared with this guy, right? We're talking about this guy at the end. Next iteration, it jumps ahead to be that one and this one. Next iteration, that one. Is it just half? And also, what have I done? Is there the last one you only need to do 1 on or something? It does it twice. Ooh. 1, first iteration, second iteration, third iteration, fourth iteration. So it's just a divide by 2. So you do 16 read lanes basically. I don't know if that's good. Doesn't sound good to me. There's one approach with a read lane. I don't know if it's good, to be fair. You're reading, essentially you're doing a, no, you're not doing a splat. Yeah, you're reading different lanes on each thread. So you're taking one vector register and another vector register with a mask, and that mask is computed dynamically, and then it will, yeah, I'm not sure what that will, because Intel basically has that, right? Yeah, there'll be like a mask where it has an index and it all. It's probably the swizzle, isn't it, really? Yeah, it's probably one of the swizzles. AMD instruction. Is it latency we want? Low latency. Right, okay, we've just gone round. Shaded programs, what is this? The 2 methods for measuring time in a shader: time, which measures cycles, real time. Access, right. Okay, so wait to access in that. Nope. I'm not sure we're going to get the instruction latency. Common floating point executing 5 cycle latency. Right, here's something here. I think I should have read cycles. This is for RDNA though. That's GCN. Different. Single cycle instruction issue. The vector instruction throughput is 1 every cycle. It sleeps away for 0 cycles. Whoa. Um, 32 lanes of right. Reading or writing in 1 cycle. So yeah, so it takes 1 cycle to read into a VGPR or something like that. Right, what is it? Okay, so these instructions work over multiple cycles to compute a result matrix. Right. Yes, that's a matrix op. Right, what is this? Index and atomic operations supply a unique address per work item, VGPRs it to the LDS. So apparently reading from LDS can be done in as little as 1 clock cycle. For wave 32 or 2 cycles for wave 64, or take up as many as 64 cycles depending upon the number of bank conflicts. Alright, it's interesting to note, but still not what we want. Oh, what is this? FMA, single cycle penalty, SALU, so scalar arithmetic is 1 cycle. What about that DS swizzle? I think it'll be using swizzle. Would it be using swizzle? I think so. Yeah, didn't quite say, unfortunately, which is a shame. But yeah, I think it's done with DS swizzle, because you just D-word swizzle. No data is written to LDS. Swizzle's input thread based on the offset. Does not read or write to memory banks. Yeah, so this is how you read from the different waves, basically. Doesn't really say the latency on it. Yes, you'd have to iterate effectively the wave size divided by 2. We gathered. It just does 2 at a time. No, that's not right. That's not right, surely. That's not right, is it? So you've got 8 threads, each doing the next one, which means... Yeah, no, maybe it's right. Yeah, because this one's doing the next one, this one's doing here, and then this thread is going to hit this one, while this thread, instead of leaping to there, will leap over to there instead. Yeah, that's right. Doing 2 at a time. Right, so that read lane is probably not a good way to do it. We want to try and see if there's a way to compare. You want to see how many threads have the same value, the same slot. Does count bits? Nope. See, we might have to do a read lane. So you'd call that function 16 times. And count up how many... right, so I'll check this one more time. So this one compares... Yeah, See, the other way is doing is writing it all out to LDS. That might be quicker than doing a rotate. You write them all out to LDS, and then you could probably just iterate over yeah, you could probably do it there and it might be quicker. Well, I'm not sure if it would actually. But yeah, something to think about. I think this is the sort of the right route to go, because we're not using any LDS memory. And we don't have to worry about multiple compute units trying to talk to each other. Right, I think I'll save this file on... Have we got anything that we're doing in here? Yeah, so let's just write this up quick. So we want to do like a 1... We sort of want to have our like 0. You want to have the models split into clusters. You have the models split into clusters. See, for animated models, not sure about that, but anyway, over... And then sort of like... then you want to essentially dispatch over each model cluster and bin into sparse grid. So after you dispatch into the grid, from there you could probably do some yeah, I think we'll sort of do some more stuff. Let's put that there. Sphere cluster count, bin sphere, unique slot. We'll need to iron out the exact plan on how it would go inside the shader. But yeah, so let's just save that as we got it. So like BVH plan. We'll load that up on Thursday. So yeah, our next be on Thursday at 8 p.m. GMT, and we'll think about this plan a little bit more. I'll see if I've got some time to see if I can find a way where we can compare across the values across different waves, and there might be a good way to do that we're not thinking about. Right. Okay, let's get rid of that. Right, let's find someone to raid. Alright, let's raid Brookazar. Okay. Oh, sorry, Brookazar. There we go. Right, have a good Wednesday and Thursday, guys. I'll see you all on Thursday, hopefully. If not, Sunday at 4 p.m. Sorry, it's 6 p.m. GMT. Right, catch you later. Thank you. Bye-bye.